Welcome to this session. In this class, we will be discussing about DRAM, which is dynamic RAM. So, in SRAM memory cell, you have learned that it requires 6 transistors. So, it takes a significant amount of silicon space. And as a result, it is having low storage density. So, in order to address this problem, DRAM was invented. So in DRAM memory cell, it consists of storage capacitor and access transistors. Binary data is stored in the form of charge inside the capacitor. The capacitor, which is in charge state, represent 1 and discharge state represent bit 0. So in DRAM, the data is stored in the form of charge in capacitor. So the storage device is the capacitor, and the capacitor requires less space for fabrication, and that is why it is having a large storage density. So but there is a problem associated with the capacitor, that is the charge across capacitor will leaks after some time. So it requires a periodic refresh circuit in order to retain the stored data. So DRAM requires a periodic refreshing of the stored data. DRAM can be implemented using 1 transistor DRAM memory cell or 3 transistor memory cell. Before that, dynamic RAM, that DRAM is called dynamic RAM. It is because of the reason that I told earlier, that because it requires a periodic refreshing after every few milliseconds. That's why it's called dynamic RAM. So now let's see 1 transistor DRAM. So you can see this is the 1 transistor DRAM. It consists of a access transistor, a capacitor, and there is a word line and a bit line. Word line is selected by a row address decoder, and this access transistor acts as a switch which is controlled by the word line, and it is this transistor which connects bit line to the capacitor. So whenever read or write operation takes place, we need to activate this word line. Then only this transistor is on and bit line is connected to the capacitor, so that you can either read or modify the stored charge across the capacitor. Remember one thing, that this is an explicit capacitor. That means a separate capacitor must be manufactured for each storage cell for data storage. In later you see in the 3 transistor DRAM, there is not explicit capacitor. At that case, the storage capacitor is a parasitic capacitance. But in 1T DRAM, this is an actual explicit transistor. Then we know the what is the charge voltage expression. It is of the capacitor. Qs is equal to Vs into Cs. I forgot to write Cs here, so it is actually Qs is equal to Cs, Vs into Cs. So when Vs is equal to 0, the Qs will be 0, and as a result, logic 0 is present in the memory cell, and when Vs is greater than 0, Q is also greater than 0, hence logic 1 is present in the memory cell. Now let's move on to write operation. In the write operation, we need to first activate this word line, then only this transistor is on. Bit line for write operation, bit line will act as input line, and it is drawn with necessary values. when bit line is 1, that is when bit line is pre-charged to VDD, the capacitor will charge to VDD, but we know that pass transistor can pass only VDD minus VTH, hence it will charge to VDD minus VTH. So the charge that is present across the capacitor will be given by this expression, Qs is equal to Cs into VDD minus VTH. So when there is a charge across capacitor, we say that logic 1 is stored bit. So when bit line is 1, logic 1 will be written onto the memory cell. When BL is 0, so when BL is 0 means the bit line is connected to ground. So what happens? The charge across the capacitor will pull down, and as a result, the capacitor discharge takes place, and the charge across the capacitor is 0, and as a result, logic 0 is stored. So this is how write to operation takes place. Next is read operation. For read operation, we need to pre-charge the capacitance that is connected to the bit lines. Actually, this is a parasitic capacitance called, usually it is called column capacitance. So this column capacitance is pre-charged to VDD by 2, and when for read operation, we need to activate this word line, that is we need word line is 1 and this transistor M1 is on. So when M1 is on, the C bit, the voltage, it is voltage across C bit is VDD by 2. What happens? The current will flows through these two capacitors until the voltage across these two capacitors became same. This process is called charge sharing. So after charge sharing, the voltage across this capacitor and voltage across this capacitor will be same. Depending upon the amount of stored charge on CS, the bit line voltage either increases or decreases slightly. If bit line voltage is greater than VDD by 2, the sense amplifier will detect the output as 1, and when Vs is equal to 0, the bit line voltage will be lesser than VDD by 2 and hence detect output as 0. So in this way, the read operation takes place. Note that charge sharing between CS and C bit destroys the stored charge on C1, and as a result, read operation is called destructive readout. Next, let's see hold operation. For hold operation, word line will be 0, and as a result, the access transistor will be turned off. Then the charge is held on capacitor, but we know that there is a problem with the capacitor as the charge across the capacitor will leaks away. So we define a hold time as the longest period of time that the cell can maintain a voltage, that is logic 1 state. That is called hold time, and its another name is retention time. So to overcome charge leakage problem, what we do is it employs the DRAM array employs a refresh operation where the data is periodically read from every cell, amplified and then rewritten. So in this way, the stored charge across the capacitor and DRAM cell is maintained. So for periodic refreshing, an external circuitry is employed which is automatically working in the background. These refresh cycles are generated by separate counters circuits in memory. So periodic refreshing means after every few milliseconds this operation has to be takes place. So for that, scheduling this counter circuits is required. The refresh rate is determined by the hold time, and it will be in the order of milliseconds. Even though the DRAM array requires additional peripheral circuitry for scheduling and performing the refreshing operation, it doesn't affect the area advantage gained by the small cell size. That means that advantage is still there, even though this overhead hardware is present. Now let's see the expression for the hold time. So for hold operation, word line is 0 and this transistor is off. So but there will be some leakage current that will be present, and this leakage current drains away the charge across the capacitor. We know the current expression for the capacitor, that is IL is equal to minus dq by dt, and which is equal to minus Cs into dVs by dt. Here this Vs is the voltage across the capacitor, and I wrote it as a Vs function of t because it is varying with respect to time. You can see this graph of the capacitor voltage. Initially it has Vmax, but after some time we know that with respect to time this voltage is decreasing. At hold time, minimum voltage for logic 1 state is present, and after this time the memory cell will be in logic 0 state. Find TH, sorry, this is supposed to be TH. Assume IL is constant, so IL is equal to minus Cs into delta Vs by delta T. Then hold time is given by TH, which is equal to Cs into delta Vs by IL. So what is this delta Vs? It is the difference between Vmax and V1. So V1 is the minimum voltage required for representing logic 1 state. So hold time can be decreased by using large capacitance and minimizing the leakage current. So that's all about one transistor DRAM cell. We have discussed read operation, write operation and hold operation. Let's move on to 3 transistor DRAM cell. As the name implies, it consists of, this memory cell consists of 3 transistors. These 2 transistors M1 and M3 are access transistors, and this transistor is the storage transistor. Binary information is stored in the form of charge in the parasitic, not capacitance. So this is the parasitic capacitance, and here the information is stored as the in the form of charge across this capacitor. So based on the charge is present in the capacitor or not, the storage transistor will be on or off. Then the pass transistors M1 and M3 acts as switches for data read and data write operations. So unlike the previous case, you can see there are 2 separate word lines. One is for read operation, read select. This will be on during read operation, and there is another word line, word select, which will be on or activated when write operation takes place. So why we have separate word lines for read and write operation is that, so when read operation takes place, for charge to not leak away through this word select line through this transistor, we separate word line, we have separate lines for the read and write operation. And also you can see these 2 lines with a bit and bit bar. Actually this bit line is for write operation, and this bit line is for read operation. Let's see the overall circuit which consisting this DRAM cell, pre-charge circuitry and read and write circuitry. So this is the overall circuitry. This portion we have seen that this is a DRAM cell, 3T DRAM cell, and this is pre-charge part, and this is writing circuitry, and from this line data is read from this bit line and is detected by the sense amplifier. So before every write and read operation, pre-charging will take place by giving high signal to the pre-charge devices, and as a result these two transistors are on, and the capacitor, this is a column capacitor associated with these bit lines, will charge up to VDD. So this before every read and write operation, these two capacitors C2 and C3 capacitors are pre-charged to VDD. Let's see write operation. For write operation, first let's look at writing 1 onto the memory cell. For that, C2 and C3, these are the column capacitance, are pre-charged up to logic 1 level. For writing operation, word select has to be turned on, and as a result M1 transistor is on. So the capacitor, the charge on C2 is shared with C1. So we are writing 1 to the memory cell. For word select has to be kept at 1. So this transistor is on. These two capacitors C2 and C3 are pre-charged to VDD, and note that this transistor will be off in this case. So this is charged up to VDD, and this transistor is on. So charge sharing will take place between C2 and the C1, and the capacitor C1 will get charged, and in this way logical 1 is written onto the memory cell. We know that the presence of charge in the storage capacitor represent logic 1 state. Now let's see write 0 operation. So in this case also C2 and C3 has to be pre-charged, and data bar will become 1, MD is on, word select is 1, and this turns the M1 transistor on. Now the C2 and C1 is pulled to 0 through M1 and MD, and as a result the charge across the storage capacitor will reduced, and in this way logical 0 is written onto the memory cell. Let's see how it takes place. So we are going to write 0. Writing 0 means this transistor is on. So current flows through this transistor. Before this operation, the C2 and C3 has to be pre-charged, and word select is made high, so that M1 is transistor. So M1 transistor is on. And now what happens? The charge across C2 and the charge across C1 will discharge towards discharge and pulled down to 0 through this transistor, which makes the charge in the C1 get discharged, and as a result logical 0 is written onto the memory cell. And after write operation, word select is 0, so that M1 is off. So now C2 is discharged to 0, so M2 will be in off condition. Now let's move on to read operation. For read operation, read select is 1 and word select is 0. So read select 1 means this transistor is on. Word select 0 means this transistor is off. C3 is pre-charged before read operation. Then based on the voltage across C1, this transistor M2 will be on or off. Suppose the C1 is fully charged, then this transistor is on. M3 is already on because of read select is high. So what happens is the voltage across C3 will discharge to ground. That is when the memory cell was storing 1. The capacitor will be in fully charged state, which makes the M2 transistor on, and as a result the charge, the voltage across the C3 will discharge to ground, which makes this bit line to 0. So when this bit line is read as 0 by the sense amplifier, it will make the output as 1. So we successfully read 1 from the memory cell. Suppose before read operation, memory cell was stored as logical 0, then how we will get 0 as the output? That is we are going to see. So when read operation, during this read operation, read selector will be 1 and word selector will be 0. This transistor off, this transistor will be on. Since 0 was present in the memory cell before the read operation, that means there won't be charge, the charge across C1 will be 0. So since charge across C1 is 0, the M2 will be off. M2 will be off means the capacitor which was pre-charged to VDD before read operation is still remains as VDD, as there is no path for discharging. So since this bit line is still VDD, data out is 1, and this is sensed by the sense amplifier and detects the output as 0. So in this way 0 is read from the memory cell. Let's just recap read operation. For that, read select is 1 and write select is 0. M3 is on, M1 is off, and C3 is pre-charged. When X is VDD minus VTH, then M1 is on and M3 is also on. So the capacitor will discharge and bit bar is 0. When bit bar is 0, the sense amplifier returns output as 1. When X is 0, the M2 is off and C2 has no way to discharge and bit bar will be 1. And hence the output of sense amplifier is 0. So that's all about read operation, and we have discussed now the 3T DRAM cell. Now let's see difference between SRAM and DRAM. In SRAM we have seen that information is stored using latching arrangement. So the transistors are the storage devices that is used in the SRAM. But in the case of DRAM, capacitors are used to store data. Therefore, in SRAM, since capacitors are not used, it requires no refreshing required. But DRAM, it requires a periodic refreshing of memory cell as the charge across the capacitor leaks away after some time. Next is SRAM is faster than DRAM, but in the case of DRAM it is having slow access speed. SRAM is expensive than DRAM, and DRAM is cheaper. So since in the case of SRAM, if you look at the size of the memory cell, it is large compared to DRAM because of many transistors, and as a result it is having low storage density. But in the case of DRAM, the memory cell consists of capacitor as the main storage device, which requires very less space on the silicon for manufacturing. So the size of the memory cell is less, and also consequently it is having high storage density. Next is SRAM is usually having less power consumption compared to DRAM, but at higher frequency power consumption of both SRAM and DRAM are comparable. So if you are asked to write the advantages and disadvantages of DRAM, you can write these points. Since SRAM is faster, it is used as in cache memory, and in the case of DRAM, since it is having a high storage density, it is used as main memory. So that's all about DRAM. And please note one thing, that when I explained the write operation of the DRAM cell, I told WS as word select, but it is not word select, it is write select. So that was a mistake. I hope you understand this class. Thank you.